Thank you very much, Sybil. It's a great honour to be here. I've been told that for the purpose of the picture, I need to stay in line with Sir Isaac Newton, and staying in line with Newton is always a very good idea, so I'll do the best I can. I'd like to talk today about three topics with the broad heading of resilience, vulnerability and transformability in the coupled carbon-climate-human system. Those three big words in the top line will be themes that run through this talk rather than being major words that I will define as we go through. What I'd like to do is to first look at some of the carbon-climate-human connections in the Earth system from the point of view of some trends, many of which we're familiar with and maybe a couple that we're not, to look at the implications of those for emergent behaviours in the system. Then in the second part of the talk, to become somewhat more quantitative and to look at the biophysical carbon-climate system at global scale. This is very much this part of the talk will be very much biophysically focused. We'll even have a couple of equations in it. But third, to change gear completely and to look at the human forces shaping the system from the point of view of stories and narratives, and I'll explain when we get to that part of the talk why these topics are emerging as important. So you're all familiar with pictures like this. This shows the interactions between components of the Earth system, including the energy, carbon and water cycles represented by the three intersecting circles in the centre, interacting with two major dimensions. On the left, something that these cycles have interacted with since the beginning of the Earth, the natural environment, its biosphere, its climate, its water cycle. On the right, the new player, if you will, in the Earth system, human societies, cultures and economies, which in the era of the Anthropocene, perhaps named in a meeting, possibly in this building, I believe that was the case, that this era is the time where human societies are exerting planet-wide influences on the natural functioning of the Earth system to rival the influences exerted by the natural system itself. And this era, the Anthropocene, is in large part defined by the dramatic growth that has happened in many of the features of human societies since the start of the Industrial Revolution about 200 years ago. And this picture gives some idea as to how dramatic that growth is. The top panels show, and can everybody see, by the way? Good. The top panels show global population and gross world product, essentially the global income, from economic history investigations by Angus Maddison and others. The bottom panel, the quotient of those two, the gross world product per capita, which in a sense is a measure of wealth or income per human. That per capita gross world product has undergone a step change in round about 1800. It's almost possible to pick the decade. Prior to that, it grew very little over the previous 2,000 years, and arguably for much longer than that. After that, it started to increase exponentially. Its rate of increase is about 1.5% per year, and it continues on that trajectory. If we look at some of the impacts of this, then three famous pictures put these impacts into a perspective. On the top, we have the forcing of emissions from, in this case, fossil fuel combustions and land use change combined on the global atmosphere. This is the emission in petagrams per year of carbon running from 1850 through to present. The middle panel is the proximate response, the response of the atmosphere, showing an increase of CO2, as we all know, from about 280 parts per million in pre-industrial times to its present value. This slide is a couple of years old, and so the present value is about 396 parts per million. The mean CO2 concentration of the atmosphere will cross 400 parts per million in a year or two's time. And the bottom panel shows the next response of the Earth system, the response in climate, where temperatures, of course, have warmed by about 0.8 degrees over that period. And we have at the moment the IPCC meeting within a few kilometres of here to organise the summary for policymakers of the fifth assessment report, which will detail that trend in enormous detail. Looking at those three pictures, a few things strike anyone. The first is that all of the curves have an approximately exponentially increasing character. And the second is that they are all, to some extent, increasing together. There's no obvious lag between them. That's a fact of some importance, I think, and we'll come to that in the second part of the talk. If now we dig into the factors that cause this dramatic increase in emissions. The picture on the left shows trajectories plotted in the way that you see shown in the cartoon at the top. What we've done is to take a resource use, and for the left picture it's energy, and for the right picture it's fossil fuel emissions. And we've calculated the per capita resource use, the resource use per person, and that's been plotted on the horizontal axis against per capita wealth, which of course grows all the time. So this is something like a plot against time, but in a lot of ways it's more revealing than a plot against time, because it shows how our increases in wealth per person are related to our increases in resource use. And shown here are the curves for half a dozen countries and the world average. Each of the circles represents 1 year, and the years, broadly speaking, track from 1971 on the left through to 2011 on the right. This data, by the way, comes from the International Energy Agency. You see here, if I use this, yes, the two circles for the world here represent the average situation for the world as a whole, plotted only at the beginning and the end of that time, because otherwise we just get a big splurb. Up here we have the USA. In red, my own country, Australia. Sweden is the light green dots here. A slightly different green shows the average for Europe. And here are China and India down at the bottom, accelerating enormously in their per capita wealth, and also with very substantial increases in per capita energy use. If we move to the right-hand picture, this now shows the same style of picture, but now for emissions. And what we see is that the two pictures are almost the same. It's rather difficult to tell them apart, with one exception, and that's Sweden. And I realised this, by the way, for the first time this morning, because I like to draw this picture afresh for any country where I'm giving a talk. So Sweden appeared on this picture for the first time this morning. And it shows that Sweden is one of the few countries in the world where there's a consistent increase in energy use, and certainly a consistent increase in wealth through the whole of this period, but at the same time a significant decrease in per capita emissions. Almost everywhere else that is not the case. And if we take the relationship between those two pictures, we get a quantity known as the carbon intensity of energy. It is the emissions per unit energy. Effectively, it's the right-hand graph divided by the left-hand graph on the previous picture. And there the special case of Sweden shows out very dramatically. Here the carbon intensity of Sweden's energy consumption has decreased by a factor of almost 3 over that period. China and India are still, as emerging economies, showing a significant increase in their carbon intensity. China showing some signs of levelling off, India not yet at that point. Europe, some decrease. Australia and the USA showing very little response in carbon intensity of energy. One of the critical points about this picture is that the carbon intensity of energy is our first and foremost quantity to tackle as we bring emissions under control without substantially decreasing energy consumption and therefore without substantially decreasing quality of life. We know that there's growth appearing, and this picture just makes that point again, pointing out the very large difference between the growth rates for four quantities: population, gross domestic product, energy and emissions, represented by the four different coloured bars, red, green, blue and black. And the difference is stark between the non-OECD countries and the OECD countries, essentially the developed world, with differences in growth rates of factors of several in all of these quantities between them. One last picture in this introductory survey concerns something rather different, and that's the growth of inequality. Here I only had data available for OECD countries. It came from an OECD report published a year or so ago, and it shows the growth rates in three different income classes. All incomes averaged together are the green bars. The richest 10% are growing at a rate given by the blue bars, and the richest 10% are the red bars. The label is incorrect there. The blue bars are the poorest 10%. And the picture that emerges is that in almost every country, over the period represented by this, which is about a period of just over 20 years, the richest 10% have been growing at rates far faster than the poorest 10%. This is a significant issue because I'm sure many of you will know of the work of Richard Wilkinson and Kate Pickett, and others have made the same point. Their book is called The Spirit Level, and in that book they trace a large number of pieces of data showing that more equal societies produce better outcomes on a wide range of measures of health, levels of violence in society, educational levels, many aspects of the social health of a society correlate well with levels of equality. And so the implication of their work, when looked at in the context of this picture, is that the growth in inequality is heading in the wrong direction. It's taking us in directions that are likely in the longer run to produce problems for many of these metrics. So I'll now change gear, the first of two significant changes of gear in this talk, and talk about the carbon climate system, the biophysical carbon climate system at global scale, looking in a way that's slightly different from the usual highly model-based approach to this system, at some of the basic ratios between responses and forcings. And the reason why this is important is that as we attempt to set targets for mitigating climate change, we need to know how much, quite obviously, to set, and some basic ideas about how responses are linked to forcings is of a great help in doing that. So I'll be looking at several ratios. The first is a ratio called the CO2 Airborne Fraction. I'll define it in a moment. The second, a ratio new in some work that we've been doing in our group and with colleagues over the last few years, the CO2 uptake rate, which is a measure of the performance of the land and ocean sinks for CO2. And the third, the relationship between warming and cumulative CO2 emissions, which is one of the major metrics that is now being used, including by the Summary for Policymakers and other parts of IPCC, just under consideration now. So just to return for a moment to the first part of the story and have another look at global CO2 emissions. This picture shows in the top panel total emissions from fossil fuels and land use change combined, and the two curves separated. The combined curve is the brown one at the top, fossil fuels the red, and land use change the green. And just focusing on the top panel for a moment, you see that the vertical axis is plotted logarithmically. This means that an exponential increase in any quantity would appear as a straight line. So this graph is a test of the extent to which total emissions and its various components obey the idealisation of exponential growth. And the answer is quite well over the 150 odd years represented in that picture. That's for total emissions. Fossil fuel emissions, slightly different from exponential. In particular, very recently, fossil fuel emissions growing rapidly. Land use change emissions, one of the few impacts of humans on the Earth system showing a definite reduction at the present, having gone down by about 30% over the last 10 years or so. The bottom picture shows the same curves, but now plotted as cumulatives, as integrals from the start of the Industrial Revolution, about 1800, to present. And of course, the integral of an exponential is another exponential. So if we see a straight line in the top picture, we'll see the same straight line in the bottom picture, certainly with the same slope. And the two dashed lines there, the grey dashed lines, have the same slope, and that slope corresponds for total emissions to a growth rate of about 1.9% per year, or a doubling time of 37 years. And that continues to be the trajectory for global CO2 emissions. What happens to all this CO2? We can construct an atmospheric CO2 budget which shows what comes in and what goes out. Above the line is what comes in, the fossil fuel emission, the orange, the pale orange at the top, deforestation or land use change, the yellow just beneath it, showing a slight decrease in recent years. Three things happen to this CO2. Some of it accumulates in the atmosphere. That's the pale blue wedge at the bottom of the picture. Another fraction is taken up by land sinks, terrestrial sinks of carbon dioxide. Simplest explanation being that plants are growing more rapidly and are accumulating carbon for a range of reasons, but one of the foremost is that CO2 is a fertiliser for plant growth. The third place that the CO2 goes is into the ocean, and that's represented by the blue bar here. And of the total CO2 going into the atmosphere, just less than a half accumulates in the atmosphere. Just over a half goes into the two sinks, land and ocean, approximately in equal proportions. The fraction that stays in the atmosphere is called the airborne fraction. So this is the accumulation of CO2 in the atmosphere, the pale blue part of that previous graph, divided by total emissions. Just less than a half. The question of whether there is a trend in the airborne fraction has been an important one over the last some years, and some work that we published in 2007 suggested that yes, there is a trend in the airborne fraction. This is a recent analysis of similar data. The data, of course, run back to the time of the start of the Mauna Loa record, the high-quality atmospheric CO2 record, started by Charles Keeling and continued since then and at many now places around the world. And that trend is statistically about 90% certain, and the trend rate is at roughly plus 0.3% per year. When we did this, the reason we asked the question was because we wanted to know if the airborne fraction could be used as a diagnostic for the performance of these critical land and ocean sinks that are taking up just over half of the CO2. And the short story is that it's a weak diagnostic, not the best available. The reason for that is that it's a ratio between accumulation and emissions, and therefore it depends just as much on emissions as it does on the accumulation, or the fraction that goes into the sinks, 1 minus the accumulation fraction. So we've recently been looking at a different metric, the CO2 sink rate, which is the sink strength per unit excess CO2. You'll recall that CO2 has increased from about 280 to now 396 parts per million, and of that extra CO2, at the moment about 116 parts per million, we can investigate the strength of these land and ocean sinks per part per million of extra CO2. And that sink strength, so is that the flux into the sinks, which we know very well from that CO2 budget, divided by the excess CO2 itself, at present about 116 parts per million. And what we see when we make this plot is a very significant decrease, a decrease in the sink strength of about 0.8% per year, or adding up to a total decrease of round about 30% over that period. And the question arises, why is this decrease happening? Just before coming to that question, I'll introduce one other major ratio that's of yet more importance in terms of climate negotiations at the moment, and that's the ratio of warming to cumulative emissions. This picture shows the plot of warming against time. The conventional data from now 3 or 4 major sources around the world, showing the increase that we know very well of around about 0.8 degrees to present. If we change the clock, and instead of plotting against time, we plot exactly the same warming data against the cumulative emissions of CO2 through the past, and that's exactly the picture I showed you a couple of slides ago, we see the plot in the bottom, and the line becomes rather close to straight. The two lines, red and green, are fits over different time frames through the data, and for the moment the difference between them doesn't matter. We observe what's sometimes called the transient climate sensitivity to emissions. This is the amount by which the climate will warm for each petagram, or each unit of CO2 that humans throw into the atmosphere. And that number is about 2 degrees per trillion tonnes of carbon. That's the source of the famous paper published by Miles Allen and collaborators in about 2009 with the title Towards the Trillionth Tonne. This is the trillionth tonne. And their point essentially, based also on model evidence, is that when this curve is extrapolated, the 2 degree point is reached when the cumulative CO2 emissions reach 1 trillion tonnes starting from pre-industrial. At the moment we've just crossed the 500 billion tonne mark. We've emitted since pre-industrial times about 550 tonnes of CO2 as of last year, and it's going up at 10 of those units per year. So this year it's 560, next year 570, and so on. So the questions we can ask about these ratios: first, why are these ratios, particularly the airborne fraction and this ratio of warming to cumulative emissions, which I'm going to abbreviate as T over Q, T for warming, Q for cumulative emissions, near constant from 1850 to present, in the face of this massive increase, this 20-fold increase in emissions? But to the extent that they have changed, why have they changed? And related questions for the future: how will these important ratios behave in the future? Do we expect, critical question now for mitigation, a continuance of this near proportional relationship between warming and cumulative emissions, and if so, why? Is it for the same reasons as that ratio has been nearly constant in the past? Now, I'm going to attempt to take you through an idealisation for this system which has some mathematical foundations, and I'm going to give you one, in fact 2 equations. when we construct a model for the Earth system of any complexity, including a global climate model, we use a large number of state variables, carbon pools, temperatures, water contents, concentrations of other gases and so forth at different parts of the system. And the number of state variables in these models can be very high, as in a GCM, 10 to the 7th or more, or it can be very low, as in some simple idealised climate models of order 10. With either of these kinds of model, or anything in between, we can do an important step, at least in concept. We can take the full non-linear model, which all of these GCMs are, and we can linearise it formally by taking the effectively a tangent to the function describing the model responses, the model response function phi, on that left picture. And when we have a linear model available, we have a rich set of resources, a rich set of analytic resources to draw from, and these provide some complementary insights to numerical modelling. And just to note that linear theories, although people often poo-poo linear theories as being, oh, it's just a linearisation, in fact they're widely used in climate science, in everything from response functions for the carbon cycle and climate through to the concept of global warming potentials for non-CO2 greenhouse gases, all based to one extent or another on linear theories. So if we do that, then we obtain a couple of insights, and these derive from the mathematical foundation that we can put into place. The first fact is a basic one, and it is that for any linear system of any dimension, 10 through to 10 to the 7th or more, if we feed that system, which is written in shorthand in the little equation there, with an exponential function of time as its input, the system will answer in all of its variables with exponential functions of time that have the same growth rate. This is mathematically provable. It's quite straightforward. And this means that exponentials can be thought of as the eigenfunctions of this system. Now, an eigenfunction for any system is a function such that if you feed it into the system will answer with a response of the same shape. And the simplest example, the eigenfunction for a guitar string is a sine wave. You feed a guitar string with a sine wave, and the system, the guitar string, will start to vibrate in sympathy with that sine wave at the same frequency. Having got that far, we can state a fairly basic theorem, which is that for any linear system, call that idealisation lin, with exponential forcing, call that idealisation exp, all the state variables, either 10 or 10 to the 7, will grow, and they'll grow at the forcing rate, not the various response rates that are embedded in the system. And if we think of the oceans, for example, those response rates might range from very fast for the shallow layers of the ocean through to very slow, many centuries, for the deepest layers of the ocean. This theorem is telling us that the rates at which all these state variables are growing are determined by the forcing rate. All the ratios among the state variables and the fluxes will approach constant values because everything is growing at this forcing rate, and that the ratios forget, that is, become independent of whatever state we start the system from at rates determined by the forcing rate. And so this immediately implies that to the extent that we can make these two idealisations, the lin and the exp idealisation, that for the coupled carbon climate system we would have a constant airborne fraction, and we see fairly close to that, a constant sink rate, that's this ratio between, that's this sink flux per unit excess CO2, and a constant ratio of warming to cumulative emissions. And we'd also see that other ratios in the system, for example, the ratio of the cumulative CO2 in the atmosphere or the land or the ocean would likewise approach constancy. So to find out the extent to which those idealisations do or do not hold, and if they don't hold, why they don't hold, we have to turn to a model. And I'm going to give you some results from a very simple model that we use in our group called the simple carbon climate model. It's a little bit like magic C, which is widely used in emissions mitigation projections. It includes all the major forcings, CO2, non-CO2 gases and aerosols, and it's simple to impose scenarios. Here I've chosen emission scenarios for the future. Shown here are the CO2 emissions, total emissions, in the top panel. Obviously the black curve is what's happened in the past. We've been there, done that. The future is represented by 5 different analytic emissions trajectories. These are not taken from the RCPs or the SRES scenarios or any of the other scenarios. They're idealised analytic trajectories, and all those trajectories have the property that the emissions decrease in future exponentially towards zero, and that the cumulative emission, the total area under the curve from the far past to the far future, can be easily constrained, and the 5 curves have cumulative emissions ranging from 1,000 petagrams in the case of the red curve, up to 3,000, the top blue curve. And you recall that 1,000 petagrams is roughly 1 trillion tonnes of CO2, which we expect to be consistent with a 2-degree warming over the next century or two. The result of these emission scenarios for CO2 concentrations is shown in the middle panel, and for temperatures is shown in the bottom panel. And in the case of that CO2, pardon me, the 1,000 petagram scenario, we do indeed reach a near steady temperature of about 2 degrees above pre-industrial. Now we change the clock, the time axis, in exactly the way we did a moment ago with our picture of cumulative emissions. And so now the clock, instead of being years, is cumulative emissions in petagrams or gigatons of carbon. And at the moment we've just crossed 500 in those units, and we head up in the future to anywhere up to near 3,000 on these scenarios, which, by the way, are quite consistent in this respect with the both the range spanned by the SRES scenarios from the 4th assessment report and the range spanned by the RCP scenarios for the coming 5th assessment report. And what we see, if we just focus on the bottom picture there, you see that temperature is increasing as the observations had suggested in the past, near linearly, all the way out to very high cumulative emissions in the future. And superimposed on this picture are the results from the 4th assessment report, just to give us some confidence that we're heading in the right direction. There, the 6 4th assessment report scenarios are superimposed with their cumulative emissions. Indeed, they do fall close to the line, and the scatter, the error bars there, give you some idea of the current uncertainties around this, this set of projections. So I'm now going to jump to the answers, and here I'm missing most of 2 papers. I'm omitting most of 2 papers and just giving you the conclusions from this work, having set the problem up. And the conclusions are like this. Why are the ratios among the fluxes and stores, particularly the airborne fraction and this ratio of warming to cumulative emissions, near constant in the past, in the face of this 20-fold increase in emissions? And the answer, in essence, is that because the carbon climate system has not too far from, hasn't departed all that far from this lin-exp idealisation, that the system is close to linear in its dynamics and the forcing is near exponential. And this would imply, according to that simple theorem that we had a moment ago, constant ratios. However, the ratios are not exactly constant, and the reasons include the following. We can look in particular at the strongest signal, that's the decline of the CO2 sink rate at about 0.8% per year, or a factor of nearly 1/3 over the last 50 years. And by progressively simplifying exactly the same model I showed you, we can identify which parts of the model or which factors are responsible for that decline. And the answer turns out to be that there are two kinds of factor involved. The first could be called extrinsic factors. These are factors outside the carbon climate system. The two factors are the fact that CO2 emissions are not exactly exponential. I showed you graphs indicating that they were nearly exponential, but they're not exactly. The difference does make a difference. And the second factor is volcanism. There have been significant volcanic eruptions through that 30-year period. And together, those two factors are responsible for about a bit under 2/3 of this total decline in the CO2 sink rate that we see over that period. That leaves other factors, two important ones, intrinsic factors to the carbon climate system. And the two important ones, first, the dynamics of the carbon cycle itself include some non-linearities, most particularly in the ocean, but potentially also on land. Second, there's coupling between the carbon cycle and the response of climate. In other words, the sinks themselves react to climate, and in some cases they will decrease their strength in exactly that sense as a consequence of warming. So these two factors we can identify in the model, and they turn out to be responsible for about 40% of the trend that we've seen in the past. These are the ones we have to watch in the future, because if those factors are causing a decrease in this sink rate, the sink strength per unit excess CO2 right now, then it is possible and important to track whether it's going to cause an increasing decline, yet more of a decline in the sink strength in future. So coming now to the future, how will this important ratio of warming to cumulative emissions behave? And the answer is, as we saw, that for scenarios which include all the forcings from both CO2 and non-CO2 gases, yes, it will continue to be approximately linear. However, the reasons for that are quite different from the reasons why it's been linear in the past. And in particular, the effects of these non-CO2 forcings and reinforcing feedbacks from these intrinsic factors, the carbon-climate coupling and non-linearities in the carbon cycle, will become progressively more important, and they will override the big factor that would cause that curve, the cumulative emission to warming relationship to depart, to sink below being linear. That biggest factor that would cause a sink, a decrease in the curve, is non-exponential emissions. And of course in future, even the most aggressive scenarios for emissions depart from exponential, because they all peak and at some point they go down in future. So they're not exponential emissions. So we have we have an attribution now for this tendency of the carbon climate system to show near constant ratios among many important components. That last one, of course, is very important, because if we're fixing a large amount of our target setting upon this temperature to cumulative emission relation, and increasingly that's become the way it's being done, then we want to know why this happens and what the dangers involved, what the possibilities of departure from that relationship are. So I'll conclude this part of the talk, and we're coming towards the finish. Yep, with a note that we have been through the Holocene, at the period for about the last 8,000 to 10,000 years, and most certainly in the period of human civilization, absent the last the Anthropocene period since around 1800, we've been in a period of remarkable climate stability, and it's possible, therefore, to become complacent about the climate system. The climate system is anything but stable in the long run. And without going through the details of this wonderful record, which shows changes in temperature over the last 800,000 years from ice cores in the Antarctic, and changes in the concentrations of CO2 and methane, and also sea level in the top panel, it's clear that through the glacial cycles, that the major cycling that's evident in that figure, that there are massive changes in the Earth's system, and that these can be triggered by quite minor forcings. So any idea that we live in a benign and stable planetary climate is something which the geological record tells us is not true. So in the last few minutes of this talk, I'll come to a completely different take on this entire story by looking at some of the human forces that shape where we're heading at the moment. And I want to focus not on economics or on politics, but instead on stories and narratives. And I'd like to preface this by telling you about an experience that we had 3 or so years ago, where a group of us were asked to write a report for the Australian government on challenges at energy, water, carbon intersections. And we thought, this is great, we've got a wonderful opportunity here. They're asking a really big picture question. So we worked away for several months, and we came up with what we thought was a good report. It had a number of principles laid out, a number of technological options. We discussed the resilience of both urban and rural systems. We talked about the role of innovation. We presented the report to a high-level government committee, which included a couple of government ministers and many senior bureaucrats. It fell completely flat. We went absolutely nowhere with that report. Since then, my ego has been partly helped because people come up to me and say, you did a really good job with that report, and I give them a hug. So why did it fall flat? Part of the reason is that the committee that we presented it to, and we, the people who wrote the report, were operating from two completely different narratives. And by a narrative here, I mean stories. A narrative is a story that guides and empowers actions. And in this sense, narratives are strong medicine. They're things that make people work hard, do things they wouldn't otherwise do, take risks and so forth. They're very powerful. They're fundamental to being human. But the unfortunate thing about narratives also is that they're independent of truth. Relationships between narratives and truth are not straightforward. We, the scientific community, have a narrative that places adherence to empirical observation very highly. We value this. There's a great deal of work which demonstrates that this is only a preoccupation of our corner of the universe. Two examples which I read very recently, some work by Kahn in 2013. Partisanship can undermine basic reasoning skills. People will flunk a maths problem, not on purpose, but they'll get the wrong answer, simply because giving the right answer would go against their political beliefs. Another study, where people are misinformed, correcting their errors with facts only makes them cling to their beliefs even harder. This is very hard for we, the scientific community, to focus on. Two broad narratives for the 21st century, and bear in mind that I'm not associating truth, objective truth, at this point with either of them. These are narratives which define the way that people conceive the world, visualise the world, and therefore act in it. The first we could call a growth narrative. That's the narrative which runs roughly that growth of the sort that we saw way back at the beginning of this talk since 1800 is what's lifted a large proportion of the world and is now lifting most of the rest of it out of poverty, improving living standards, improving health outcomes, all sorts of good things. The second is a sustenance narrative, which basically says we humans are now starting to run into the walls of our petri dish. The Earth system is reached the point where we are having significant impacts upon it, and where if we do not pay attention to the fact that we are having exponentially increasing impacts on the Earth, within a couple of doubling times, and you'll recall that the doubling time for most things is somewhere around the 30 to 40 to 50 year mark, we'll be in real trouble. So the hypothesis that I would like to, in a sense, test with you is that narratives are actually subject to evolutionary dynamics. They can be thought of as meme sequences, memes in the Dawkins sense, ideas that propagate, sequences because they go together, these memes stick together, and they propagate through the evolutionary mechanisms that underlie all evolutionary emergence in biology and ecology, but also in technologies and economies. Diversification, selection and adaptation. If that's so, then evolution and the evolution of our narratives is a process that we can perhaps understand. We can maybe influence it. We certainly can't control it. These processes are not controllable in a mechanistic sense. Why can we influence? Because we are used to influencing evolution in other settings. We breed plants. We manipulate our evolutionary environment by changing selection pressures. So the implications of this would be that in shaping our shared future, the evolutionary contest between narratives, and I've highlighted two broad narrative families here, is just as important as the dynamics of the natural world and will have just as much to do with the outcomes as the dynamics of the natural world. I'm a natural scientist. This is the second part of this talk is my home base. This is not my home base. However, I recognise the importance of these things. And also that we need to guide the evolution of these resilient narratives, narratives which can withstand shocks and assaults thrown at them, that will empower the transition to a society that is simultaneously sustainable but also improving global well-being. So, to summarise our place, we know that we are part of a long story of evolutionary emergence, a rather unusual part of it. We also know that everything in this story is dynamic, that there's no stasis, that sustainability in the sense that we're looking for it involves wrestling with continual dynamism. We know that our planetary system has responded, I think it's fair to say, fairly benignly to the changes that we have imposed on it through the period of the Anthropocene. The reason I say it's fairly benign is that most of these important ratios are still linear, still showing linear relationships. However, this is not guaranteed to continue for a wide variety of reasons. So our future, we have finite planet pressures, which we all know about. We have narratives which I think it's fair to say are easily visible as shapers of the society we're in. I've highlighted two, the growth and sustenance narratives. They're evolving entities. They're not static. They change. And the future will depend on new narratives emerging from this evolutionary process as much as on natural dynamics. And perhaps a way of encapsulating this new grand narrative might be something like reimagining growth that we all need as humans to be consistent with global sustenance. So I've gone through a number of topics and I thank you very much for your attention.